Okay, in previous class we talked about what we talk about the three phenomena that is important to polymer, which is the crystallization, the phenomena that we taught in the previous class, phenomena. They are crystallization, and then we have the glass transition, we have the melting temperature. So the crystallization is basically the phase transformation of the melt polymer to the solid polymer. So basically you have melt polymer goes to solid polymer. So that is basically crystallization lah. And then melting is just simply the opposite for that lah. So the melting is from the solid to melt lah. Solid polymer to melt polymer. And in between this thing, in between this extreme, you have what we call the glass transition temperature. So in between this, so this can go here, this can go here. So in between this, you have what we call TG, or glass transition temperature. So we call it TG. For crystallization, we call it TC. TC. So melting is Tm, temperature where it's melt. And for glass transition temperature is Tg. Okay, so the word glass here, as you can see here, the word glass here, meaning that the polymer share the characteristic like a glass, which is hard. For example, let's say you have like a glue stick like this. Let's say you have this glue stick. This is a polymer. It makes like a stick. So you can see here, it's stable, meaning that it's retained its shape. The reason why this polymer can retain its shape is because the amorphous part, remember the polymer have the both crystalline and amorphous part, and normally the polymer have both. So the amorphous part in this polymer, they are restricted in motion, they cannot move. So that's why it can retain the what we call this shape lah. But when you try to melt it, for example, if I may, if let's say I put some candle here, so you can see, right? You can see in front. You can see, right? Okay. So that is the candle. If you try to melt this, what happens if you put here? What now happens is basically the amorphous part start to wiggle around, start to sort of like vibrate here and there, rotate here and there, and eventually it will melt. Until certain temperature, it will melt. So here, so you can see over time, it will melt lah. It will melt like that. It will melt like that, and you get something like this. Okay. Okay. So let me put here. Let me put here lah. So you can see from the glue stick that we see just now, you can see there are three parts. So you have the glue stick, something like this, and then the melting. So the glue stick become melt lah, melt like that. So it deform. Melting, the term melting is basically when you have the crystalline part of the polymer start to become disorder. That is melting. When the crystalline part of the polymer start to become disorder. The glass, this part, this is this. The glass transition temperature is quite unique for the polymer is because here the structure still retain its solid structure, but this becomes soft. It becomes softer lah. It becomes soft. When something becomes soft, when you have polymer that is soft, it's not melting yet, but the mechanical performance for this is totally different than this. Meaning that if this you can sort of like, it's still solid, this still solid, it becomes softer solid. This only unique for the polymer. If you see what we call other thing, for example, like metal, they don't have this TG. They don't have this TG. They are straight away from here. Suddenly it becomes like this. Okay, for metal, from here straight to here, it doesn't have this TG. So to give you the idea, just let's see the behavior of the ice. So let's say you have cup of ice. Just to give you the idea what happened to the metal. Because metal is crystalline. Remember, metal is crystalline. Ice, the ice cube, is also crystalline. crystalline, meaning that the water molecule, the H2O, they arrange in certain order. So that's why you get the ice. So if you see the ice, if you try to draw the what we call the graph, the graph where you have this, you have what we call, you have heat, and then you have the temperature. Let's say you have the beaker or the glass, and then inside the beaker you put what we call, you put the ice. And then you try to heat it. Okay, just now we heat the polymer, but now let's see what happens when you heat the crystalline material like the ice or the metal. You see the difference in terms of behavior. If you try to heat this and then you put the thermometer inside, let's say you put the thermometer inside here, what will happen? You will see when you heat the thing, the temperature, the heat is basically the harbor lah, is basically the energy that you put into the heating. The temperature is just a measure. So when you heat the thing, basically you increase, you give the energy, the heat to the ice. So this, it will sort of like increase somehow like that. Okay, as you can see here, you increase the energy, and then the temperature also rise a little bit. Imagine this is, the ice is basically 0 Celsius, right? So when 0 Celsius reach, what will happen? Suddenly something happened at 0 Celsius here. Imagine this is negative 20 Celsius. Okay, negative 20 Celsius is the temperature in your freezer lah. In your freezer is around negative 20, negative 15. Okay. When you try to heat the ice from the freezer in the cup, what will happen? The temperature start to rise. Negative 20, negative 15, negative 10, and so on until it reaches 0 Celsius. So let's say I put here temperature here. Let's say here we have a 0 Celsius here. But here something unique happen is that you keep increasing the heat, but there are no, what we call, there are no temperature change. Okay, what does it mean is that this thing, when you try to heat it, is, let's say you have the clock and then you put 1 minute, it's still 0 Celsius. After 2 minutes, it's still 0 Celsius. So even though if you do something like this, even though now you have this glass, this ice start to melt, something like this, and you keep heating it, you still see the what we call, the thermometer give you the 0 Celsius, even though you see there are some melting happen. So after 3 minutes, it's still 0 Celsius, until at one point everything is become liquefied. Only then you can see the increase of what we call increase of the temperature, until everything liquefy like this. And then you have this thermometer. Only then you can see some increase in temperature lah. You start to see increase in temperature. So that's why here at 0 Celsius here, you will see there are no increase in what we call in temperature. So you can see something like this. Okay, you keep adding heat, but there are no change in the temperature. The reason why is because when you want to melt something, it requires energy. So every energy given by the heat goes to the melting process, and none goes to the increasing the temperature. Because to increase the temperature, you need energy also. This heat supply will increase the temperature, but at this point, that all the heat is used to melt process only, in the melting process only. So that's why you don't see the temperature rise. And until everything become liquid, then you get what we call, you start to get this increase again. So this part, we call it what? We call it latent heat lah. Latent heat. The word latent means hidden. So it's hidden because all the energy is used to melt process, in the melt process, not to increase the temperature. But once thing is already melt, then only then the energy in the heat is used to raise the temperature. So if you look here, there are something unique here, not unique, I mean there's something that is normal. You can see the slope here and the slope here is different. You can see the slope here is much steeper, okay? Because here, remember, this is the ice part. This is the water part. Let's say I put here the division, this ice, the water part. The ice, everything have their own heat capacity. Heat capacity is the ability for the material to absorb heat. It's also applied to everything lah, ceramic, metal, polymer, whatever. But I will discuss this first, so later on I will put everything in place where we want to discuss the ceramic. So here, ice and water have their own heat capacity, the ability for the material to absorb energy. So the heat capacity for the ice is around 4.12, if I'm not mistaken. So this is 4.12 or 4.2, I don't remember lah, 4.2 kilojoule. So that is energy per kg Kelvin. So meaning that it needs 4.2 kilojoule of energy to increase the temperature of 1 kilogram of ice to 1 Kelvin up. Meaning that to raise from 0 to 1 Kelvin lah, meaning that 1 Kelvin different lah. So this is 4.2 Kelvin. Here for the water here, not the ice. Sorry, this is the other way around. So the water is 4.2 kilojoule per kg Kelvin. Okay, but for the ice is basically half of it. It's around 2.1 kilojoule per kg per. Okay, so this is basically what we call the heat capacity, the ability of the material to sort of like absorb the heat, absorb the energy. Heat capacity. Every material has their own heat capacity. Normally, the molten phase, they have higher heat capacity than the solid phase. So what does it mean here is that you need double the energy, the heat, in order to rise the temperature compared to the ice. You need twice the energy for water to increase the temperature to 1 degree Celsius compared to the ice lah. Understand or not? You need like, so meaning that the water will, the temperature for the water will increase slower than the ice. You get or not? No, not get. The water, because it need, for example, let's say you have negative 20 Celsius to negative 19 Celsius. So this for the ice, and for the water, let's say from 20 Celsius to 21 Celsius. So this for the water. So you see the difference is 1 Celsius. The difference is 1 Celsius. So you need to take, because this require more energy than this, so it takes twice longer lah. It's slower lah. It's slower because it require more energy in order to raise 1 Celsius. So that's the thing lah. So that's why you can see this thing you can see here. The what we call the heat needed is a little bit more than here to raise the temperature from one point to another point. So that's what we call the explain why the slope here and the slope here is different. Okay, so this is for the ice. Ice is a crystalline material because the water molecule is arranged in periodic manner. Metal also crystalline, so metal also behave like this, meaning that if you have metal, if you try to heat it, it will not, it will reach a certain point where the temperature will not rise until everything is melted. So metal also have this latent heat and so on. But for the polymer, it's different. For polymer, if you have polymer, let's say I put here polymer. If you have polymer, let's say I draw something like this. Okay, if I have polymer, so let's say I put heat and also the temperature here also, temperature here. For the polymer, the temperature keep increasing. If you increase the temperature, it keep increasing like the glue stick just now, it keep increasing, but they don't have the latent heat. They just sort of like increase like this. They don't have the latent heat part, and they increase like this. So this part here, we call it TG. Okay. So it will keep rising in terms of temperature until it melts. Okay. For the crystalline material, we know this melting part lah. But for the what we call for the polymer, the temperature doesn't undergo this latent heat phase. It just keep increasing from here until it's melt. So as you can see here, this and this have a different slopey slope lah. The same idea like this. The molten polymer have higher heat capacity than the solid polymer. So that's why you can see it need a higher heat, absorb higher heat in order to raise the temperature compared to this lah. So you have this TG here, and there are no break. Here you can see there are break. In fact, normally people draw like this. People draw something like this, like the dash, I call dash line, to show that there are break between this and this. But for polymer, it just goes continuous. So that's why you see something like this. Okay, if you have a temperature probe, you will see there are no like sort of like no constant of temperature happen. It keep melting. If you look here, you see it's black. Huh? Why is black? Why is black? Carbon. Huh? Carbon from where? Why is black? Is it degrade or what? Rhoda, why is black? Why when I do this is black? Because this black come from the wax. Okay, wax. This is a lily ni. Wax ni. Wax also a polymer. Okay, wax itself is a polymer made from hydrocarbon. You know hydrocarbon. So they make this thing, the crude oil. They make this wax or lily lah. They wax. So what will happen when you try to heat things? When you try to heat the what we call to heat the candle. This is wax. Wax is basically hydrocarbon. You learn hydrocarbon in organic chemistry. It's a chain of a carbon, and then you have ash, whatever lah, hydrocarbon. So basically, when you light the candle, what happens is that this when you try to have the lighter, you give the fire. This give off heat, and the heat will sort of like melt this thing. Melt this candle. That's why you see there are something like a lekuk here in the candle. So if you look there, this thing, this fire doesn't sort of like burn the entire thing. It's just burn on the top. The reason is that the thing happened is not because of the wax itself, the solid wax. It's happened because this wax is melted. When it's melted, it will vaporize. It will vaporize. The wax, the hydrocarbon, become gas. Solid hydrocarbon. This is gas hydrocarbon. So it will vaporize. So you have this vaporized, meaning that that is hydrocarbon lah. So you have hydrocarbon which is full. And then you have oxygen around you. You have oxygen. And then you have oxygen. And then you have heat from this thing. You have heat. Okay. When you have these three things, the oxygen, the fuel, and heat, you get the fire. So this is what we call the triangle of fire. So in order to make a fire, you need three things: the fuel, the heat, and the oxygen. So you have this thing, you get fire. So that's why you see the fire keep there, because what happened is this: the wax keep melting and evaporate. The hydrocarbon keep evaporating, meet with the oxygen, and then you have heat. So this hydrocarbon act like a fuel, and then you get the fire. So this is more like chemistry lah. So that's why you don't see the candle. The candle doesn't flame like this. They must always. This doesn't touch. This thing doesn't even touch this thing. So that is the chemistry of the candle lah. Anyway, so that is the thing. So here the black thing come from the hydrocarbon, the soot. This come because of the incomplete combustion of this thing. Okay. Normally, you have two types of combustion. Meaning that combustion, you have incomplete and complete. Incomplete meaning that this thing, the ratio between this is not right. So you have like unused hydrocarbon. So that's why the unused hydrocarbon goes here. If you have complete combustion, for example, like this, you can see the blue flame, the blue flame. So this coming from this propane, whatever butane or whatever this thing, the fuel. So it become blue is because the air and the heat and the fuel, they are mixed in the correct ratio. So everything is utilized. So that's why you don't see any jelaga or whatever lah. But for this, the hydrocarbon inside this doesn't meet with the oxygen and heat with the perfect ratio. That's why you see that some leftover hydrocarbon goes here, the one that is not reacted. If I try to sort of like melt this thing with this, you don't see the black thing lah, the what we call the black stuff. The black stuff you don't see lah. Okay, even though so you don't see the black stuff. But if you can see here, oh, I have this. I forget I have the camera. Okay. So you can see this is melting. Remember, this is melting point. This melting, when you melt, is a melting point. But I don't know whether you can see or not, the color here is not white like this. It's a yellowish. Because after melting, there are points that we call degradation temperature. Because let's say you have solid, and then you go to TG first, and then go to TM. Let's say this solid polymer, you have melting temperature. If let's say you supply the polymer with the more heat than is needed, then you get the TD. TD is basically degradation temperature. Okay, so typically when you want to reuse the thing, you want until here only TM, melting temperature. But if you give more energy than is needed, then this thing will become what we call cannot hold. It will degrade lah. The amorphous and the crystalline part inside this polymer, they degrade. So that's what we call a TD. So that's why in order to melt, to reuse the polymer, you cannot just simply melt using this thing. You need to what we call to melt it at the melting temperature, because above that you have TD, degradation temperature. When TD is still melt, but you see the yellowish thing, and that is not what we call in terms of mechanical performance, is weaker than the if you melt only lah. So that's why we have this glue gun lah, this glue gun. So for the glue gun, this is the glue stick for the glue gun. So if you look here, this glue stick, this specific glue stick is high temperature glue stick. Because even though you go to the shop and you see a glue stick like this, there are two types of glue stick. For example, first you have a high temp glue stick, glue gun, high temp glue gun, and then low temp glue gun. Okay. So when you are trying to melting this glue stick, you need to know which glue gun you need. So this to show that each polymer have their own melting temperature, even though it look the same. Okay, so that's why you learn this material science. You cannot just use, if you see something like this, you just melt using any glue gun. Sometimes you see the small one, the small glue gun. The small glue gun, typically they call it low temperature glue gun. So that glue gun, for the small glue gun, I don't bring it here, but the small glue gun can go up to 130 Celsius. For the high temperature glue gun, it can go to 195 Celsius. So what is the temperature signify? This is temperature where it can melt the stick. Okay. So the low temp glue gun, the normal glue gun that is normally you see, let me open. Do we have this thing? Let me open first. Glue. Glue gun. Glue stick. Okay, glue gun. Okay, so let's go here. So you can see there are two different type of glue gun. So let me open this thing. Okay. So as you can see here, this a small glue gun is what we call the low temp glue gun. It can only hit the stick up to 130 Celsius. So this stick is high temperature stick. So if I use this, it cannot melt this thing. Okay, this glue gun, the low temp glue gun, is used for the craft normally when you want to sort of like attach two polystyrene together and so on. When people do craft, they normally use this thing lah. The advantage of this is that it is safe, it's relatively safe, the temperature is not so high so that you don't risk burning your hand. But this thing is very hot. Okay. One of the advantages of using the high temperature stick or with the high temperature glue gun is that you can sort of like bond more material than that. For example, this thing can only bond maybe polystyrene, something like that, normal thing. But this thing, it can give a good bond even to the metal or the wood. For example, I have the wood here, and then I try to sort of like what we call glue this thing together. So you can see this thing. So let's say this is two what you call two. So I just do that, like that. So I just do like that lah, and then so this is melting lah. This is melting at 165. So it's not nice that, but it's okay. So this, okay. So what happened now? It start to crystallize again. So now when I do like this, it's cool. The air cool the matte plastic, and crystallization happen again lah. And the advantage of the glue gun, you just it's very quick lah. The thing is very quick. And this it take some time to give a good bond. So instead of using nail and so on, now you can have a joint like this. But of course, this joint is not as permanent as when you use nail or screw. But at least, if let's say you want to make a prototype, then this is a good thing lah. This is quite strong. Let I give you. Let it set for a while lah. Let it set for a while. Okay, so you can just try to this thing lah. It's pretty strong lah. Okay, you can pass around. So that is basically the advantage of using this high temperature glue gun. If you use the low temperature glue gun, you cannot be strong as that lah. You can try to what we call to kepak lah. Okay. So that's one thing about the glue stick. Okay. So we learn now. Let's recap for a while. We learn about the difference between crystallization, melting, and TG. Especially the TG is a unique thing that happened to the polymer. So you need to know about the graph, the melting graph for crystalline material like the ice or metal. You also need to see the graph for the polymer is totally different than the graph for crystalline material because polymer have this amorphous and also crystalline material. This happened because of the amorphous part. TG is basically the rotation of the amorphous part, while melting, TM, is basically the disorder of the crystalline part. Because polymer have both, then polymer show two temperature, TG and TM. But for crystalline material, they show only TM only, melting temperature. We learned also about the example of this thing using the candle and also the glue stick. We also learned about the heat capacity, and then we also learn about different type of the glue gun, the heat stick. There are two type of heat stick: high temp glue gun, low temp glue gun. It's a same polymer. It's a polymer. When you go to the shop, you try to buy this thing. It look the same, but it behave differently. So material science is like that. Sometimes you see something very similar, but it's not. Okay, so that is part of this. So we done with that. So you can see now during our discussion about this TG, temperature, melting, or whatsoever, we see now that one of the major drawback for the engineering polymer is that the heat. It can sort of like distorted by the heat. So one of the classification of the polymer is based on the heat. You have thermoplastic and you have a thermoset. So for that, I need to rub this first. Where is this thing? So thermoplastic is what we call is a polymer that you can melt and remelt again. The glue stick that you see just now is example of thermoplastic. So let me put this thing. Okay. So let's talk about the the classification of the what we call of the polymer based on the temperature, the based on the behavior when it subjected to the temperature. So you have the polymer. You can classify also based on the behavior upon temperature, either thermoplastic, and thermoset. What is thermoplastic? Thermoplastic is basically polymer that melt upon when heated, eventually melted and hardened when cool. Okay, so that is basically not definition, but this is just a rough idea about what is thermoplastic. So you can see you have melt. So this is TM. You also have a polymer that soften lah, not melt. That soften first. That soften when heated, eventually melted, and then hardened when cooled lah. So this is basically TG lah. This part is TM, and this part is basically TC. Okay, when you try to heat this thermoplastic or thermoset beyond its melting temperature, you get the degradation. So we don't cover lah that. But this is the sort of like definition of thermoplastic: polymer that can soften when heated, eventually melted and hardened back when cool. Okay. So in other words, the thermoplastic can be melted and remelted again and again, and you can get what we call, you can reuse again and again lah. For example, like this glue stick. For example, it's melt, but then it still become like a glue stick again, like this. Okay, it's hardened. Okay, so that is definition of thermoplastic lah. The polymer that can be reused, melted and remelted again and again. So we talk about thermoplastic first before we talk about the thermoset. Okay, so of course there are a lot of thermoplastic in the world, so we cannot cover everything. So we will cover some thermoplastic that is common in your everyday life. Okay, have you ever see for example, that bottle, right? Can you see at the bottom of the bottle, Rauda? Can you see the triangle? Do you see the triangle? Yeah. So normally, sometimes you see a triangle, the small triangle, underneath the bottle of the plastic Tupperware, whatever. So that is basically resin identification code. So RIC, resin identification code. Resin is basically a generic term for the polymer precursor. Okay, resin is a generic term for the polymer precursor. What make the polymer lah? I mean the precursor. I mean the original thing lah. So resin identification code is developed to why you have this code. So you see something like this, 1, 2, and so on, right? So this is developed in order for what? In order to sort and recycle, to help sorting and recycle. Because if you want to recycle something, let's say you have 2 thermoplastic, you want to recycle that, you need to separate first. You cannot melt them together because different thermoplastic have different melting temperature. So for example, you have A and B. So A is melt at 190 and B melt at 80 only. Let's say you have these two things, 2 polymer A and B. So if you try to mix this together and you try to melt, in order to melt both, you need to melt more than 190, right? But if you try to heat this thing, these 2 mixture together, the B will be degraded. This A is okay, it will be melted, but the B will be degraded. So that's why you need to separate when you recycle, because each thermoplastic have different what we call different melting temperature. The reason why different plastic have different melting temperature is because the plastic, each plastic have different ratio of the amorphous and crystalline part inside that. So that's one of the reason lah. So the sort, that's the reason why you use this RIC to sort and also to recycle. Recycle means that you can reuse again. So meaning that whatever under this RIC is basically thermoplastic, because you want to recycle. Thermoplastic, as I said, you can reuse again. Mean that you can remold and reuse again and again. So that's why under the RIC, typically it's a thermoplastic lah. Not typically, it's a thermoplastic. So you have basically 7. 1, 2, 3, 4, 5, 6, and 7 lah. 7 of the what we call the RIC. So the one stand for PET. The one is for PET. So PET is basically a polyethylene. It's a polyethylene terephthalate. And then you have what? You have after PET, number 2 is HDPE. HDPE. Number 3 is PVC. Number 4 is LDPE. Number 5 is PP. This is polystyrene, and this is for others. Okay, so PET, polyethylene terephthalate. So from the word itself, you see there are ethylene and also terephthalate. PET and also terephthalate. So the terephthalate is basically something like this lah, something like this C, and then you have this benzyl group, and then you have this C, you have O, and then you have ester bond. And then you have this ethylene part. The ethylene, you know, is something like this lah. CH, H, C, H, and H, like that. And then you have what we call the something like this. Say this, you have something. So this is basically the monomer, not monomer, the repeat unit for what we call for the poly PET lah. So the PET, the example for PET is like Raudah bottle there. So that is like a plastic bottle lah. Plastic bottle like this. The what we call this thing. This thing. If you look underneath, you will see number 1. Number 1. You see number 1. So this body. This body is basically PET. If you can see here, one of the properties of PET is that it's flexible. It's flexible. So one of the properties of the PET is that it is flexible. It's flexible. Flexible meaning that it can sort of like resist shatter. It's shatterproof. In other words, people call it shatterproof. 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 So if let's say you sort of like jatuhkan ini, is shatterproof lah. So because it have a good mechanical properties. Okay. And also it have good barrier properties. Good barrier properties. What does it mean is that you know the air around you, there are air and also gas and whatsoever. So this PET have a good barrier properties. So the air from outside cannot enter this thing lah. I mean it's hard for the air outside to enter this PET. So that's why people use it to put a drink or so on. And also it's pretty cheap lah. So in fact the PET is one of the most produced plastic around the world lah. PET. It also has high strength to weight ratio. High strength to weight ratio lah. Meaning that is strong lah. It's strong. Okay, so that is PET. Example is plastic bottle. So HDPE is basically what? High density polyethylene. You know polyethylene, you learn about the organic chemistry. So polyethylene is like this. C, H, and then that's it. And then you have this repeat unit lah. So this is basically high density polyethylene. The word polyethylene here, ethylene is this thing. So the repeat unit is ethylene. So high density meaning that this thing, let's say you have the chain, it will something like this. 1 chain, 2 chain, 3 chain. So it's dense. It's dense with each other chain. So this is high density polyethylene. So plastic bottle, the Raudah plastic bottle, this is PET. The body is PET, but this thing, the cap is HDPE. If you look, the number at the cap is 02. Yeah, it's different. It's 02. This is 01, this is 02. So that's example of what we call the HDPE lah. So example for this is basically typically this HDPE is translucent. It's translucent. So normally example for that is like a milk jug bottle, and also the bottle, this cap lah, this cap. Okay, so you see the color for that cap is a little bit stronger. If you feel this thing cap is a little bit stiff, rigid. It's more rigid than this thing. Okay, so the properties for the HDPE is that it have it's rigid lah, translucent, and also it's rigid, and it have this rigid character lah. Okay, so now PVC. PVC stand for polyvinyl chloride. So basically what we call the structure, the repeat unit is basically CC, H, and instead of H you have here, you have Cl. So because that is chloride, so you have something like this, and then you have this thing lah. And so example for this polyvinyl chloride is your pipe lah. Your pipe is basically the example is pipe lah. Pipe. The pipe yang normally you see in the something. Do I have the pipe? Something like this lah. The pipe, the white or the normally in grey color, but sometimes you see the white pipe that also from PVC. So that is PVC. So example is a pipe, and then the characteristic of that is that it's highly is good resistant to acid, base, salt, grease, oil like that. So that's why people use this for the pipe, for the sewer pipe, because you dump everything in your sink, so it goes to the PVC pipe, but the PVC have their good resistance, so that's okay. Okay, for the PVC lah. Okay, so next is basically LDPE. LDPE is basically low density polyethylene. So basically it's the same like that. It's the same like this. So you have a repeat unit like this also. CH, H, and not H. So you have something like this same. The difference between this LDPE and the HDPE is that the molecular packing. So if this is HDPE, the what we call if this is the HDPE, the LDPE normally they have branch. So because you have a branch, when you pack, it cannot go sort of like dense like that. So this, when you cannot pack very dense, it have low density. That's why we call it low density polyethylene. Example for this is a plastic bag lah. Plastic bag. Normally you go to grocery store, they give a plastic when you buy something. That is what we call. That is basically the low density polyethylene like this. This plastic bag, when you buy something from Shopee, they do something like this, and then you see there are number 4 here, right? Number 4. So that's why this is high density polyethylene lah. So what is the characteristic of this thing? It has more branching. It got more branching than what we call HDPE lah. HDPE. So it's weaker lah. In other words, it's weaker than HDPE lah. And then next you have the PP. You have the polypropylene. The polypropylene. So this is polypropylene. Okay. Polypropylene. You see the word here, propylene. Mean that prop. Hydrocarbon, you learn in organic chemistry, there are 3 things. 3 carbon. So basically it's like this, CC. And then you have H, you have H, you have H, and you have another C here, polypropylene. So CH3 here. So you have something like that. So this is like a repeat unit for the polypropylene. Example of polypropylene is basically a container, microwavable plastic container, for example, when you buy this thing, let me put here. Okay, let me this thing. Okay, for example, here, let's say plastic container, plastic PP. So you get plastic PP. You get something like that lah. So you get something plastic like that lah. This thing, container, something like this. So this is PP. So one of the characteristic of PP is basically first it can resist heat. Okay, you can see it's microwavable. Right? So it can, one of the properties of the PP is that it resists heat distortion. So meaning that it can undergo a high temperature lah. So it can, example of this, it can also meaning that it can be microwavable, and also it can be autoclavable. So autoclave is basically a machine that used to sterilize the thing in the lab lah. So and also it have good fatigue resistant, meaning that you know the tic tac cap. Nak tengok tic tac. Tahu tic tac apa? Tic tac cap. So this tic tac. Nak tengok kan tic tac. So this cap is made from the PP. So because you open close, one of the characteristic of the material is that it can fatigue, letih. Macam you sekarang letih kan? Penat kan? Berapa jam? Letih. So sama juga macam ni, dia letih juga. So it's letih. So this PP have good fatigue resistant lah, meaning that even though you open close many times, it's still okay lah. Okay. So be like this, be like PP. So this made from the PP. So that has two characteristics, the main characteristic of this what we call PP. And then PS is basically polystyrene. So the monomer for that is basically ACC, ash, and then you have ash, and then instead the styrene, you have styrene. Styrene is basically this thing lah, the benzyl group. Okay, we call it styrene or benzyl or aromatic group. Okay, in organic chemistry you learn that thing. So that is basically the repeat unit for polystyrene. So polystyrene, example of polystyrene is basically plastic kitchen utensil. Example like this. So we have something like this. Okay, so like this. Okay, so this is basically PS. If you see, you go to HS to eat this lunch. So you take this thing. You see at the back it shows number 6. Okay, normally kitchen utensil, the cheap kitchen utensil like plastic is polystyrene. One of the properties of this is that it's brittle. Okay, so polystyrene, even though it's cheap but it's brittle. Polystyrene is brittle. So that is plastic kitchen utensil, like this lah, like that thing, like sudu garpu whatever thing lah. But this is one drawback, but advantage is that it's cheap lah. It's cheap. So polystyrene, so that is basically the solid polystyrene. Sometimes you can turn that polystyrene into foam. You can turn polystyrene into foam. Okay. So polystyrene foam have two categories. Either is EPS or XPS. E here mean extruded, expanded. X here mean extruded. Okay. So example of EPS polystyrene is the one that you see like this lah. The normal polystyrene that you see in the styrofoam, we call it styrofoam lah. So if you look this EPS closely, you will see it made of what? It made of bit, right? It made of these small bits. So if you try to open this, if you take one, you will see that it's made of the what I call the bits. Okay. So the bit here, you can see here they are what we call the hollow. The bit itself, this bit, they are like a lot of air inside. Not air, I mean that if you look inside the bit, you will see something like this. Something like this lah, again and again. So this is what we call the closed pore. So mean that the bit, if you see one bit of this under microscope, the pore is closed. Okay. Even though the pore is closed, but if you have this many bit, the pore is closed, meaning that the water cannot go inside. But this bit, they are, for example, they are sort of like the gap here. So the water can go inside here. So that is EPS, expanded polystyrene. It's made from the bit of this closed pore bit, and then it's compressed. It's sort of like made into mold, but there are like a gap here, so it's allow the water goes. Meaning that if I have what we call the syringe with the water, if I put here, if let's say imagine I have syringe with the water, I try to push the water inside, you can see the water coming out here and there. So EPS, so that is EPS, the normal polystyrene that you see lah. The XPS is extruded. Extruded here meaning that there are no, everything is closed pore. Everything is like this. Everything is something like this. So there are no bit like that. There are no what we call, there are no bit, and there are no gap. There are no this gap in between. So this thing is more rigid lah, more rigid. That is XPS. If you compare the SPF and the XPS versus EPS foam, you will see something like this. Okay, normally something like that lah. Mana? Tak ada gambar cantik lah. EPS for some. Okay. So you see here, this is example of the what we call the expanded polystyrene, the normal polystyrene. So this EPS, this XPS, they sort of like more rigid lah, more rigid. If you look here, the what we call the SPF, there are no gap. Everything is closed pore. But for the EPS, even though the bit is a closed pore, but there are gap in between here. So that is basically the difference between the EPS and XPS lah. I don't have the XPS here to show you, but if you go to Mr. DIY, you find something that is in the blue color like this, you try to picit-picit dia. Jangan beli, picit je. So you will see it's quite rigid lah, quite rigid compared to that. Okay, so that is the XPS. So the characteristic of this polystyrene is basically it's brittle, it's cheap, and it's basically poor barrier to oxygen and water lah. Water, especially for EPS, lah. And then the lastly, we have the others. We have others here. So the others here, basically other thermoplastic that is not these six lah, not PET, HDPE, PVC, LDPE, PP, and PS. So I will explain just a few things. So example for others, polyamide. Polyamide example for others. Polyamide is another name for nylon. We learned about nylon in the previous class. So polyamide is basically the other name of the nylon. Nylon. We learned in the previous class about the condensation polymerization of the nylon. So refer back to that. So that is polyamide. Polyamide can be melted and remelted again. So it fall under the thermoplastic. So nylon, example for nylon in your life is basically like what we call like the, do I have? No, I don't have the thing. Okay, like this. Nylon, apa panggil ni? Apa orang panggil ni? Dipanggil apa ni? Apa orang panggil ni? Tie, cable tie. Okay, so cable tie is made from the nylon lah, for the nylon. So this example is basically cable tie. Cable tie. Okay, then we have also what we call, so the properties for the polyamide, they have what we call good mechanical strength lah, good mechanical strength, and toughness. Okay. So later on when we talk about the mechanical properties, we will talk about the strength and toughness. And then that is polyamide, one of the example of the 7 lah, one of the under 7 lah. And then another one is polycarbonate. Polycarbonate. So basically, polycarbonate, example of polycarbonate is when you have helmet that whizzer, whatever the name, the thing is made from polycarbonate. The helmet example is helmet whizzer. Helmet whizzer. Okay. And also example also CD and DVD. You know CD and DVD, right? You still see, right? CD and DVD, right? This polycarbonate, the properties of polycarbonate, it have a good impact resistance. One of the main characteristic of polycarbonate is have good impact resistance. Good impact resistance for polycarbonate. So let me put it down. So good impact resistance. So that's why people use it as a helmet whizzer, like that. And then maybe the last for this others is basically PTFE. Okay, PTFE, polytetrafluoroethylene. Polytetrafluoroethylene. So basically the chemical structure for this is basically like this, CC, and then instead of H you have F here. So that is basically PTFE. PTFE. So one of the characteristics of the PTFE is that it's highly inert. It's inert, highly inert to any environment. Inert meaning that it doesn't react with other things. Example for PTFE is like this. This is PTFE. This is PTFE. This is PTFE. So you can see this thing, people use this to make a magnetic stirrer in the lab. So you can see example for that is the magnetic stirrer in the lab. So that thing in the lab, later on you go to the lab, you will see this thing. So this is made from this PTFE. So properties for that is that it's highly inert. So you dump any chemical, it's still like this. It doesn't react. So that's why people use this thing. But this is expensive. So when you buy something like this, it's expensive. When you buy something like this, it's expensive. It's highly inert to any chemical reaction, and also it's also quite slippery. You can see this slippery. If I put down and then I test to slide my shoes, it's just slippery. So you just feel the slipperiness of that thing. So another what we call another properties is slippery lah. Slippery, meaning that it have low coefficient of friction. Low coefficient of friction. It's slippery, meaning that it have it doesn't have, it have low friction, it's have less friction compared to other material. So that's why people use this thing as a Tefal, non-stick pan. So you can see this Tefal. So this thing, they coat it with the PTFE. That's why when you fry the eggs in Tefal or non-stick frying pan, the egg doesn't stick on this thing. You can just move like that, right? They coat this thing with the PTFE. So PTFE also, you can see PTFE tape. Example of PTFE tape is this thing. So that's also PTFE made from the PTFE lah. It also have high thermal, what we call high thermal, good thermal resistance, meaning that it can resist high temperature. For example, you can use this to fry anything up to 260 Celsius. So another characteristic is that have good thermal resistance lah, good thermal resistance. So in polymer world, that PTFE, in terms of when you do research in the lab, that PTFE is most desirable polymer lah, but it's expensive. That is pretty expensive lah. But that's what we call king of the polymer. Some people call it king of the polymer lah, because it's very inert. You can do anything without any reaction, and then the thing and so on. So once you learn everything like this, why you learn everything like this is that you know all this thing is a thermoplastic, but material that you see, for example, let's say you have a petri dish, petri dish. Let's say you have a petri dish. Have you seen petri dish before? You see, right? This petri dish. Okay, this the plastic petri dish, because you have also glass petri dish. This plastic petri dish, if you try to buy this plastic petri dish, if you want to buy for your research, when you do a final year project, or you, let's say you go for the research field later on, if you want to buy the petri dish, there are many material that is used to make the petri dish. Some petri dish is made from the polypropylene, but most of petri dish is made from the polystyrene. Okay, there's two things. Let's say this thing. Most petri dish is made from the polystyrene. Because why? Because it's cheap. Polystyrene, one of the advantages of using polystyrene is cheap. But then the problem with the polystyrene, it can have low, what we call, it cannot resist temperature, high temperature. It will soften. So meaning that if you want to sterilize this thing, you cannot put in the autoclave. When I say autoclave, do you understand what is autoclave? You know, like autoclave. Pressure cooker, you know pressure cooker. So basically, autoclave is like that. You put something, you close the thing, so the pressure increase. When the pressure increase, the boiling point reduce lah. Meaning that instead of boiling the water at 100 Celsius, if you put water inside the pressure cooker, you can boil the water less than 100 Celsius. So that's the idea. Because when you try to pressure cooker, when you close this thing, the pressure inside become low. When pressure is low, then the water, if let's say you have water molecule on the surface easily goes to the air lah, meaning easily detached from the surface. So that's why if you go to the mountain, you try to heat the water, boil the water, you can boil the water less than 100 Celsius, maybe around 90 Celsius is already boiled. But in the sea level like here, if you try to boil the water, you need to reach 100 Celsius. But in pressure cooker, you can reduce the pressure, meaning that you can boil this thing at lower temperature lah. So autoclave is something like this thing lah. So you can sort of like heat the thing is higher than its normal lah. So because if you buy the polystyrene using the if you buy the petri dish made from polystyrene, you cannot put in autoclave, because when people want to do like this to make the agar and then to grow something on that thing, you need to make sure this agar must be sterile, cannot have any bacteria and so on. Because if not, then if you try to put your own bacteria, then other bacteria will come and colonize the thing. So that's why in order to make this agar, we call it agar, you need to make sure you need to autoclave first. Everything must be sterile. But if you use this petri dish made from the polystyrene, then you cannot autoclave it because it will deform upon heat. So that's why some people also, some company also sell petri dish made from the polypropylene. And one of the characteristics of the polypropylene is that it can resist heat distortion, so you can autoclave that. So autoclave, when I say autoclave, normally you can go to 120 Celsius. Normally when you try to boil the water, that water is boiled, the temperature you put the thermometer is maintained at 100 only. It will not go beyond 100. But if you put in the autoclave, it can go up to 120, 100, whatever lah, depend on the pressure lah. So that's why people use autoclave. Because not bacteria, fungus, if you try to boil some of the resistant fungus or bacteria, not die, especially fungus lah. So that's why you need to very high heat lah. So that's why people also, some company also sell this polypropylene petri dish. But this polypropylene petri dish, even though it can resist temperature, is more expensive than this. So that's why later on when you go for second year, third year, fourth year later on, when you be in the lab, you try to recall back what you learned today, and you see, even though something looks similar, because polystyrene petri dish and polypropylene petri dish look similar, both look similar but have a different properties. Same like this thing, like the what you call this bottle. This bottle, where is the thing? Where's the this thing? You see this bottle is made from the PET. This bottle made from the PET. This bottle made from the PET. But this cap is made from the HDPE. This plastic here, that plastic is made from the LDPE. So you can see there are many, what we call, many type of plastic. So this is HDPE. So you have the label here, that is LDPE, and the bottle itself is PET. So that's cover the thermoplastic part for today's lah.